All right, welcome to CS267. Today I'm going to talk about something a little different, which is cloud computing. And I'm going to talk a little bit about how some of the differences between a cloud and HPC systems and how they're programmed, but also give you an idea about how some of the programming models that we use on the cloud. And I've used a bunch of slides from other people who have actually given this lecture before in this class. So Matej Zaharia, who's now on the faculty at Stanford, and Shivran Venkataram. So cloud computing really took off in the phase of big data, where big data was all the rage and all the hype. So those are some of the cover articles from that time period. And that really led to this explosion in cloud computing because a lot of companies couldn't afford to put that much computing, the computing that they needed on site, or a number of different sort of economic factors, the size of and the power requirements for the data centers and so on were growing. So it was really about data, and this is a quote from of course, the founders of Google here on the anatomy of a large-scale hypertextual web search engine. So it's a little old, but the storage space, they said, had to be efficiently used to store the indices and optionally the documents themselves. And the indexing system had to process hundreds of gigabytes of data efficiently. Now that's way off in terms of the size. It's much larger today, but nevertheless, that's what they were focused on, is how to deal with this large index set that they needed to build for indexing the web. So just to give you some idea of the size of some of these large data sets, Facebook's daily logs are over half a petabyte per day. And sequencing data, or for something like the sequencing read archive, is over 35 petabytes. And the Google Web index is at over 100 petabytes, what they store today, what they collect today. So this and this graph on the left, which is from the IDC, looks at the growth, the projected growth of, and based on current, historical projections of data from a number of different subdomains. So entertainment, that dark orange at the bottom, which is, you can see, continuing to grow rapidly. A lot of other image and video data that's not just from the entertainment domain. And then productivity data really means the kind of data that we have on standard servers and desktops, all this stuff, your email and things like that. I don't know that I would call that a productivity tool, but nevertheless, email, spreadsheets, PowerPoint, all that. And then embedded data coming from sensors, which they're projecting to really increase in terms of the size of that data set. So we're seeing and continue to see huge growth in all of these digital forms of data that are being collected. In science, and genomics, of course, is one thing that comes up in science. I'll say a little bit more about that. But at something like the national labs, we also run scientific experiments, and their data rates are growing faster than Moore's law as well. So these are something like the advanced light source, and there are a number of specific light sources that are shown here in the different hash and dot marks here. But the main point is that some of these things are about twice the pace, the synchrotrons or free electron lasers, in terms of their brightness, which then corresponds to the amount of data that is being pushed out of them, is growing at double the rate of Moore's law. And so you can see that these detectors that are being used in some of these advanced scientific instruments are also producing data rates that are higher, faster than Moore's law. Now, this is not a data rate issue, but the human genome, the sequencing technology is also improved over time exponentially. And so this is a graph that's really nice. It's on the NIH website, and it's updated every 6 months, I believe. You can see that the cost, and so this is on cost, which is a little obviously different than a data rate, except that it is related to what people can afford to do, and they sequence more and more if they can afford to do more and more in a scientific or medical research community. We've seen this, for example, in COVID, where the ability to sequence the genome has become, the viral genome has become increasingly important as we try to understand variants. But here we're just looking at the cost of a human genome, which has gone down to around $1,000 for a human genome. You can see it's leveled off here in the last few years. There may be some other technology coming in play, but it's been a little bit flat for a while, but had a huge drop there, where it took $100 million for the first one. And so this just sort of summarizes these growth rates just based on, these are curves are just based on the average growth rate, annual growth rate. And just to try to sort of put it all together, red is that detector from something like the light sources, the sequencers, that's based on the cost, but is sort of assuming that the amount of data that we're going to sequence is growing roughly in proportion to the drop in cost. And then you may say, well, we don't really care about processor speed because these are big data problems, but the memory line, of course, as we've talked about before, has grown even more slowly than the processor rate. Now, the other place where this increase is coming up, and I think both Aiden and I may have shown this graph, but just to remind you that the amount of computing that's required for training neural nets has also been growing exponentially. It increased by about 300,000x between 2011 and 2018, looking at these two specific instances, AlphaNet and AlphaGo Zero. And in that same period of time, the top 500 grew by less than 10x. And so this was 300,000x compared to about a little under 10x. So what do these cloud computing facilities look like? Well, I'm sure you've seen these pictures, but there's a picture of a big data center that is storing one of these types of commercial clouds. It's an enormous facility, larger than the types of facilities that we're even storing the supercomputers in. And I'll say a little bit more about that later. Now, one of the problems, of course, that even these cloud providers have had, in spite of the fact that reliability is absolutely one of their top priorities, have been outages. So there just are some of the headlines of various famous, large cloud providers having their system, their entire cloud service in a particular region or more broadly go out. I think this is a Google one that was a crash and resulted in a worldwide outage. And some of these others are somewhat more localized, but nevertheless, because people are accessing this all around the world, you can have huge global impacts of these kinds of outages. And this is a nice list of sort of practical experience of running building a new cluster. This is from Jeff Dean at a talk that he gave. So Jeff Dean from Google, talking about what are the practical problems that you have when you install one of these large new clusters in a data center. Well, you have problems with overheating, the PDUs, the power distribution units failing, the racks have to be moved around for some reason, you have to rewire the networks, bunch of rack failures, other just racks that seem to sort of misbehave in certain ways, and network maintenance, routers, various problems in the network that have to be addressed, individual machine failures, so individual node failures, and then that are around 1,000, and then thousands, so even more hard drive failures, as well as a bunch of other, flaky problems. Now, one of the things that you might not think about when you're running this is if you're running a highly reliable cloud service, you also need to distribute it physically. And so they, of course, have more than one data center and more than one location, so that if there's a hurricane or an earthquake or a tornado or whatever, or flooding or a power outage in one area, that they can shift the load relatively rapidly to one of the other data centers. And they do a lot of replication of data even across the data centers to make sure that they have that level of resilience. Well, that brings up another problem, which is the wide area network. So these networking problems on this list really are about the local area network, the data center network that connects all of the racks together, all of the machines together in the data center. But what you might not be aware of is that you have to worry about things like sharks attacking the under ocean network cables. By the way, these are very difficult to repair because you really can't just sort of go and dive down and go and fix this cable. And you may think, well, what can a shark do to this kind of big cable? Well, they can break through the outer coating, ground the line, and it causes problems. There's a nice video of this that this image is from on YouTube. I realize it's a little fuzzy here. So, adding to Jeff's list on these long distance links, he said are things like sharks, wild dogs, dead horses, drunken hunters, all kinds of things that come up out in the network. And from having been overseeing ESNet, the wide area network for the DOE labs, I can tell you that some of those kinds of physical infrastructure problems are really significant, whether it's, I think what we had was an explosion in a manhole in New York City in the streets that took out one of the labs actually off the network because there was a simultaneous failure from there was redundancy to each one of the labs, but 2 simultaneous network failures was all it took to take the lab offline for about a day. So, okay, so that's a little bit about, what these cloud centers maybe look like. I'll say a little bit more about the facilities too later, but how do we program these things? So this is something, and I know a few of you are looking at this in your final projects, looking at some cloud programming model. And I will say that over the years in this class, we've had a lot of interest from students in doing final projects that use one of these kind of cloud computing frameworks. And this will be also tell you why we're a little bit cautious about having you do this unless you're really thinking carefully about performance and parallelism. Because as you learned, going back to even homework 1, if you don't pay attention to your single node performance, you can lose an order of magnitude or 2 or 3 before you even get to looking at the parallelism. And since this class is predominantly about parallelism and performance and how you get performance out of things, that will come back to be an issue here when we talk about the cloud. So the programming model, I will refer to it as a data parallel model. It's loosely coupled, so it's kind of loosely based on this idea of data parallelism, a set of data parallel steps in a program. There is going to be a data flow graph that will connect these different steps together. And but it's a pretty restricted programmer interface that makes it fairly easy to use. It's fairly high level, and it hides a lot of complexity underneath it. In particular, it handles failures of the nodes and some of the locality optimizations, as well as some load balancing issues, all inside of the runtime system of these cloud programming models. And it basically says, you as a programmer say, here's an operation, run it on all the data. You don't worry about exactly where the data is and therefore where it has to run. And you're sort of saying implicitly, if something bad happens, go ahead and retry running this operation at another point. So very high level. It was originally envisioned in this programming model. And here's the paper by Jeff Dean and then by also Sanjay Gemawat on MapReduce, the original idea and the original implementation of it called Hadoop. And so this came out in 2004, and they used it for building the search index for web search engines and algorithms like PageRank, and some computational problems as well. And it was an open source, Hadoop was an open source implementation actually at Yahoo and Facebook as well. So the MapReduce was originally from Google. So what does the idea of MapReduce look like? Well, it's pretty simple. You can map a function and you can do a reduction with a function. So you're assuming that the data is all stored in some records that have keys and values. So a very databasey sort of style to it. And the map function is going to take a key and a value and map and apply it to a list of these values. And then the reduction is going to take one of these functions that is also applied to a list and produce something that is also could be a list. Okay, so here's an example, a really simple example of word count. And at a high level, we're going to find our mapper function, which is just going to say for every word in a line in a file, we're going to split that line by, say, spaces. And so that the split function, the split method here is going to split it into words. And you're going to then output a word with, which just has the value 1 associated with it. And then you're going to do a reduction on that and sum things up by the keys. And so that'll match all of the words that are the same, all the matching keys will get added up with the 1 and give you a sum of give you a count of the number of occurrences of that word in the file. So here's how this kind of simple program executes. You've got some input like this text here in green or in the green boxes, the quick brown fox, etc. So you map that and it is going to apply that logically to all of the data. So for example, the data is spread out over these different disks here. So we've got three disks. And so this first piece of the text is stored on the first disk. That map function then produces the set of pairs, the key value pairs, the 1, brown 1, and so on. And then those all get reduced then. So there's a big communication step where they all have to come together. And that's where the addition happens. And so then you end up with the word count coming as the output. So, what really happens in one of these cloud environments, this is still at a very high level, but you submit a job into something that's called the job tracker here. and it automatically splits up the work based on the data that it's going to be accessing and where that data lives, and it will send it out to a bunch of these different tasks, each of which will be a map task that will be, and they'll be scheduled on locally on some machine with some local disk associated with them that's got the data on it. So kind of one of the key things that's different about this than what you've seen in this course is that in this map reduced model, if a task crashes for any reason, that it will it'll retry it on another node, and if the task fails over and over again, and that would suggest that maybe there's something really fundamentally wrong with the way the task was written, then it will end the job. But it'll retry it because there might have been a hardware failure or some kind of transient error that caused it to fail once, but isn't going to cause it to fail the second time. And so that automatically gets repaired. And let's see. So and this is so this requires that the code is deterministic, and that so that you don't care what order things are what order these different nodes are executing the different parts of the code. And it also implies that it's fine to rerun this. So if a node crashes, then you need to relaunch the current task on other nodes. And in order to get the inputs, the file system has to have replicated the input values so that there isn't just one copy of each one of these green pieces of text. It's actually been spread out. There's multiple copies of each one of the pieces. So there's an interesting comment here in chat that I'm going to just read. It's also worth mentioning that most of the times these node and task failures happen because of data skew. In other words, if you have too much of a particular key in the data, and all the pairs of the same key will go to the same execution reducer, which will cause it to overload and to get an out of memory exception of some kind. So I didn't know that that's an interesting piece of what happens in practice in terms of this load imbalance, that if you have a whole bunch of keys that all match that are going to end up going on one node, then you're going to end up with too many tasks on the same node, and that will cause it to run out of memory. So that's interesting. Now, it also turns out that even if a task is running very slowly, that is, as a straggler, that the system can launch an extra copy of that and hope that maybe there was a transient issue that also caused that task to be slow, that it wasn't something inherent in the task computation. And so it can then take the output of it, whichever one finishes first. All right. So this MapReduce is a great abstraction, very high level. You can do a lot of things. You've seen some of this. I mean, once you've programmed with, even in MPI, with doing just independent computations, you can easily turn those independent computations into the map step. And then you've seen things that use reductions. And this is an even much more general form of reduction that we've got in this case. And so most of the real applications, though, require multiple of these MapReduce steps. And so, for example, the indexing pipeline is 21 steps. You can see some of the other examples of things like PageRank is tons of steps and so on. So this is really, although this is a very high level of abstraction for programming, it seems like a great way of hiding a lot of the complexity of these distributed clusters and the failure issues that you have inside of them, as well as the communication, the data movement. So when you're used to programming in something like MPI, you really see that, or UPC++, you see that that's a lot of that complexity is hidden here. However, the MapReduce programs themselves can still be pretty spaghetti-like. So if you've got something like 21 map and reduce steps, you have 21 mapper and reducer classes, and there's a bunch of other boilerplate code that gets wrapped around it as well. There's also issues with the lack of type safety in the original MapReduce because, and you've seen something like this in certainly in MPI, where, or actually when you're programming in GPUs as well, you take some nice higher level data structure that maybe has some types associated with it that you understand, though you're programming, say, in C or C++, but nevertheless, you take that and you pack it into bytes, for example, and you then lose a lot of the semantic information. And if you make an error in that packing and unpacking code, it's really hard to debug. And there's the same sort of spirit here, which is you don't really have this type information inside of the original Hadoop model. And the MapReduce model also only provides a single pass of computation. So really the semantics rely on the fact that you're writing the data out to the file system in between the different MapReduce steps. So now think about your 21 steps. There you're going to have a lot of file IO in order to execute that. So 21 or 20 steps of IO that are unnecessary, maybe in between the different steps of execution. So it's especially expensive for apps that reuse the data, especially, I mean, that is relative to what they could be doing if they kept that data in memory. So that led to the design of Spark. Some of these observations. First, about programmability, they wanted a clean functional API and to be able to do parallel transfer, what they call transformations on collections that really, because it's going to be written in a functional style, it really means creating one transformation, one collection that is a transformation of another. So you're not actually modifying or transforming the collection itself. I would have maybe said derived one collection from another, but nevertheless, that's the idea. And that allows you to reduce the amount of code by a significant factor. And then also building in a higher level language with a strong typing in it, such as Scala, R, Python, and so on. And from a performance standpoint, the advantage in Spark is going to be not putting things out in disk between every step of map and reduce, doing a set of computations in which the data all lives in memory, and then also being able to do optimization across the operators. So this is what the original MapReduce, so this is not Spark code, but in Google MapReduce, this is what the word count example actually looks like when you write out all the details. I gave you sort of a high level picture of what the mapper and the reducer look like, but this is actually what the code looks like. So instead, if you are writing this in Spark, you end up with code that looks like this. You just have you've now got this object-oriented style. So you're taking a file and doing a mapping on it of something that's splitting the lines, and then mapping something. You can see this looks analogous to what I showed earlier, but with much less code than on the previous slide, something that takes out each word and puts a 1 next to it and then does a reduction with a plus operation and then saves the counts in an output file. And what does this correspond to in terms of performance? Well, here are some higher level algorithms. So iterative algorithms like k-means clustering and logistic regression, where you would be doing things over and over again, at least say 10 times in the, and that leads to all of this file IO and the map and the original map and reduce model in Hadoop. And so you can see orders of about an order of magnitude or more speed up here from going from Hadoop into Spark. So that was a tremendous advantage in Spark in terms of being able to get this performance improvement, even though you're actually now in kind of a higher level, safer programming model because you've got types built in when you're programming in these other languages with Spark. And so how does Spark do this? Well, it's built on this concept of a resilient distributed data set, or RDD. So these are at least logically immutable. That means that we're not going to be able to modify an RDD. An RDD is going to be partitioned across the different nodes, but it can also be cached in memory for fast reuse. And then you can transform something, which means build a new RDD out of an old RDD, and then you can do actions which compute results that get returned. And so the intermediate RDDs are not really considered the final results. And so there's a certain set of restricted kinds of shared variables you can also have, so that you can do broadcast. So think of that as say a read-only variable that's shared broadly, which will be implemented as a broadcast, and then a variable that is going to be written by all of the different parts of the program, so it can be accumulated into. So here's something, a little example that's doing log mining. So we start out with our base RDD, which I guess maybe I hid that slide, but anyway, so this coming from the HDF file system, so the Hadoop file system, and so we've got this text file that's being written from it, in Spark, and then we derive from that or transform it into another RDD which has all the errors. So we're just grepping on the word error in that, and then looking at each one of those and splitting it by each line that contains an error, splitting it by tabs, and then at that point there's something that's really a performance optimization in the code that says I'm going to cache that messages RDD. And there's the base one showing up now. So then what's the next thing that we can do? Well, we can filter. So we want to look for a particular error message that contains the word foo inside of that, and then count the results of that. Now, at this point, up until this point, we've sort of said what the program is going to do. This now requires some action that we actually have to produce an output. And so that's going to cause these workers to get spawned to actually perform each of these tasks. And so each of the workers on its own subset of the data will perform the grep for error, the splitting of the lines by the tabs, and then they'll have to do a reduction in some way, hopefully in the implementation, a local reduction followed by a global reduction of the results for each one of those words. And but then this cache operation also says to cache the messages RDD in the memory as opposed to on the disk of each one of those worker nodes. And so now if you then do another count operation on a different key that you're looking for on bar, then it can use the cache copy, and that will be much faster than the first instance. And so that can return the results there. So this resulted in, for example, a full text search of Wikipedia can be done in under a second, and where it was running in about 20 seconds when the data was living on disk. So it had some repeated operations on the transformed RDDs, which made it much faster when that data is sitting, when you've cached it in memory. But you have to, explicitly put in your program that hint about caching. And you search, it can search a 1 terabyte database in about 5 to 7 seconds versus 170 if it was on disk. So really, once again, enormous speed ups from this. So this just sort of gives you an execution idea of how Spark is getting those kinds of speed ups even on those iterative algorithms. Now, one of the key pieces of MapReduce and Hadoop was this idea of fault recovery. And the RDDs have to, they're still preserving that idea of being able to recover from faults. And their RDDs are going to track the lineage information so that they can reconstruct any lost partitions. So there's this, inside of this step, it has to really keep track of how did you get this mapped RDD, say, out of the original input. And so as long as you can reconstruct the original input, and for that, we're going to make sure that the data is replicated, then we can still recompute the intermediate results. And so if you lose something, then you will recompute that task. So here's just another example of Pi in the Java instance of Spark. There's a, you can see the add operation and then parallelize using this filter. This is the Pi example that I think I talked about in the UPC++ lecture. You're just throwing darts at the unit circle. So you're computing x squared plus y squared, making it less than 1. And so, yes, we obviously have a Spark expert here in the class. So Jem also mentioned that you can now make this even faster using data frames. And I will mention there's a few slides on data frames inside of the PowerPoint deck. If you look on for this, if you want to just see a simple example of data frames, I just decided in the interest of time not to present those today, but we do have, you can look at those, and you can certainly find information online about data frames, which is another way of optimizing this. Kind of looks more like a database operations. So other RDD operations that you can do, map, filter, sample, group by key, etc. And then also these various operations, these actions that you can take, such as doing collections, counts, etc. And then you can save the output file, one of these RDDs, as a text file or as a Hadoop file or whatever. So that would force it to the action to actually happen there, even though you haven't, say, gotten a scalar value out. And here's just and I won't read through this, but so you can get a sense of what the different interfaces look like in each one of these 3 languages, at least. There's no Scala here, but there's Java, Python, and R, just to give you a sense that Spark really does, it has been embedded in some of these other very popular languages that give you strong type checking, but each of these operations kind of looks the same, but I mean, has a slightly different version depending on, for example, the count operation here in R looks a little bit different. Okay, so underneath Spark, there is a fairly complicated job scheduler, and that is capturing the dependency graph of the RDD, and then it pipelines the different stages into the functions into groups that are the stages of the pipeline. And this is aware of what caches are available so that it can do locality optimizations, and it is aware of where the data is partitioned across the file system so that it can minimize the number of shuffles, the amount of data movement in between the nodes. So there are other things. So I guess data frames were one of the things that were mentioned, but in addition to that, there's higher level libraries that have been built on top of Spark. So things like graph libraries, database libraries, SQL, machine learning libraries, mlib and TensorFlow on Spark, things like that. So there's a lot of different higher level things. So great sort of productivity tool, and allows you to really, because it runs on the cloud, you can run this on very large data sets. So it was really a huge productivity boost to people that were analyzing very large data sets to be able to run this on something like Spark or Hadoop, but now the faster version Spark on the cloud. All right, so I'm going to sort of switch here and talk now a little bit about the comparison between this sort of Spark programming model on top of cloud hardware and what you've seen more of in this class, which is programming in an HPC model, such as, let's say, MPI on top of an HPC system. So a lot of people ask about this, and actually, to me, it's a little disappointing that there's actually such a disconnect between the cloud computing community and the HPC community. I think a lot can be learned on both sides of advantages that we've got. We've got this very high level, highly fault tolerant model on the cloud side. We've got very high performance, lightweight, kind of close to the metal, but very good performance on the HPC side. So both of them are learning a lot from each other, as we'll see. So we're going to start by looking at the hardware. This is what Google hardware looked like in 1997, sitting in somebody's office, I think at Stanford or something. And so it really started with a really, really modest, you didn't need a data center for this. NERSC at that same time frame, so that was in 1997, as I said, in Google, and in NERSC in 1996 already. This was a Cray T3E supercomputer, a distributed memory supercomputer. I think I've mentioned it before, maybe one of my favorite architectures. It had DEC alpha processors, which were standard commodity processors, but had a little bit of specialized hardware around each one that made the network very fast. You could directly read and write into registers called E-registers associated with each one of those processors. So you could really make things like UPC run very fast on a Cray T3E. And there was 100 terabyte data archive. This was the robot, the tape archive that lived at NERSC at the time. And there's still big tape archives there, although they're not nearly as beautiful because they're not round anymore. They're big rectangular robots. So Google in 2001 then got a little bit bigger. It started, it needed some clusters, and their goal was to make the hardware as cheap as possible. So they bought commodity CPUs, they bought lots and lots of disks because this was all about big data, and they bought a pretty low bandwidth network because, again, they were focused on low cost and they just wanted whatever would work for the problem at hand, the lowest cost sort of system they could get to handle this size of data and these problems that they were working on. At the same time in 2001, so NERSC had a system from IBM called Seaborg, and this had power, I think 5 processors in it. These were pretty fast processors. So these were some of the highest processor rates, these IBM high-end server processors that you could buy at the time. And so a very different sort of philosophical model about how you put an HPC system together. You go and buy the most expensive processors that are the fastest that you can find, and then you put them together and into these fairly dense cabinets. Now this was still an air-cooled system, and clearly the previous one you saw that one was also air-cooled. So there are some pictures of then some of the, series of supercomputers over time that hit the first named sort of performance number. So the first megaflop machine was a CDC 6600 in 1964. The first gigaflop machine was in 1985. The first teraflop machine was in 1998. And the first petaflop machine was in 2008. So there's a pretty good succession here of, I guess we had 20 years between the first two, and then after that we were doing pretty well at one kind of a factor of 1,000 every 10 years. We have not yet, although we're well past 2018, we do not yet have an exaflop machine, although we're getting close. As I've talked about, the Fugaku machine is around, is it 400 petaflops. So we're, almost within a factor of 2, not quite, of that. And we will, and there are certainly people working on building machines within the next year that will be an exaflop. On the other hand, at the same time, clouds grew, and in some sense, clouds grew even more quickly and have grown to enormous size where they've got data centers. Oh, this is a picture of a data center, I believe, in Oregon. And this one, it has, 10,000 machines, individual nodes inside of that. And we think of these as machines as opposed to nodes because of the fact that it's got these disks, right? They're really like standalone compute machines. They've got processors, they've got memory, and they've got disks associated with them. And I'll come back to this point. The supercomputers do not have disks on each one of the nodes. And then, for latency, they've got this RAM cache. So because of the fact that even though they've got local disk, they're really worried about the fact that these disks are slow. And so they put big memory on these systems as well. So these are really optimized for big data, right? Because of the disks and, lots of disks per node, and then the lots of RAM per node. And the other thing they need to worry about is the network between the nodes. And this is looking at all of the network traffic coming from one rack. And this is the intra-cluster data traffic. So you can see that a lot of the traffic is happening within a cluster. And there's the backbone is this darker blue that's up here at the top. That would be the kind of core of the network. But there's a lot of this network happening within the cluster, but not within the rack. So within the rack is this orange down at the bottom. So you can see you really do need a pretty high bandwidth network in order to deal with this kind of network traffic in the cloud. So the data center networks, I think that in those early photos of what Google looked like, they didn't worry too much about the network topology. Over the years, they started taking ideas actually from the HPC community and building things like things that look like hypercubes, this B cube, or the fat tree network, which is similar to what we also see in the HPC systems. And they, were doing a lot of research around this, trying to make sure they could get full bisection bandwidth because of what you saw on that previous slide, that a lot of the data is actually flowing all the way across the data center in the intra data center. And here's a picture for contrast of Corey's networks, which I think Aiden talked about in the MPI lecture in terms of what this topology actually looks like. It's this tightly coupled network inside of each one of these nodes and each slot in this picture on the right, and then this kind of all-to-all connectivity graph, but not at the same. It's not fully connected all-to-all across each one of the nodes. That's just much too expensive in terms of the number of cables. But you've got pretty dense networking and then a little bit sparser at the top. All right, so how does this hardware actually compare today? And this is a nice study that was done by your GSI, by Julia Goody. So you can maybe jump in and correct me if I mess any of this up. But she looked last year at the and recently published a paper or put together and on comparing the performance of the cloud and the HPC systems. So let's see. So it actually goes back to the title of the paper is kind of looking at the past 10 years and changed, I actually co-authored a paper back in 2011. This was when I was at NERSC and as the NERSC director, and there was all this hype about cloud computing and saying, oh, cloud computing was going to replace HPC, blah, 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 and we didn't need to have HPC centers anywhere more. And so we actually received some funding to build a prototype cloud, which was called Magellan. It was spread out over 3 labs. It wasn't fault resilient, which is an unfortunate use of that particular prototype. I think we maybe demonstrate a little bit of sort of very specialized fault tolerance with a job that could move across the 3 different sites, but it wasn't engineered to hide that fault tolerance in the same way that the commercial cloud is. So at the time that we looked at that report, there were a bunch of benchmarks done, and what we found was that the cloud networks that we had access to, so I was looking at things like AWS, were very high latency networks, and they didn't have the same bandwidth as either, but the virtualization overhead, so because you can run multiple jobs on a single node, there was a fair amount of overhead on that as well, and there was performance variability on the different nodes, partly because of this virtualization issue. And that meant if you're writing, say, an MPI application with fairly frequent barrier synchronization, it could run really slowly. And also that kind of for that same reason that you didn't have a batch scheduler. So in practice, the people that were running these experiments, and I have to admit that wasn't me, said it was very hard to even launch the jobs because you would grab a couple of nodes and then you had to wait until you could get access to a couple more nodes, and then you would get a couple more nodes. And all the time, by the way, you're being charged for all the nodes that you had requested because you were sitting on them, even though you hadn't been able to actually launch the parallel job. So there have been some other studies over the years that look at each one of these different, at sort of this period of time, but even as recently as 2018, lack of low latency networks was one of the challenges that was still identified in one of these other reports. So Julia has looked at, what do these things look like now? And she looked at 4 machines. The Cori system, both the Haswell and KNL partitions of Cori, and 2 AWS configurations, what's called R5 and C5. Now, these are both high-end configurations of AWS, and the Xeon Platinum, as it's called, and sorry, that's the processor type. So these are you can see the processor types. The Xeon Phi is going to be a bit of an oddity in this study because it was a somewhat more specialized processor. The others are more standard looking Xeon, Intel processors. And these were intentionally chosen to be kind of somewhat comparable in terms of the size. Now you can see there are differences. The memory size, for example, varies. So the C5 system has memory size that's comparable to the Haswell, whereas the R5 instance is going to have much more memory, about a factor of 4 more memory. Okay, so those are the systems, and then what you can see from this is that the Cori Haswell and the R5 performance. So this is the first thing to look at was what does the peak performance look like for a compute intensive problem? And for this, she chose the LINPACK benchmark. How does the performance compare? And so this is the theoretical peak in dark orange and the LINPACK peak in the lighter orange. And you can see that there's a much bigger gap in Cori KNL and an AWS C5. And whereas the others get much closer to their peak performance. And so what happens when so the others, I guess, as I said, had a much bigger gap, and that's, you don't utilize the cores as well. I think on the KNL, there's some real issues even for something like dense matrix multiply in terms of getting that performance out because of the dynamic clock speed scaling. So once you start running that, it will downclock that kind of compute intensive problem, and just being able to feed all of the arithmetic units in the memory system. And now the other point that comes up, and this has come up in at least one of the other studies, and is an important observation about the cloud versus an HPC system, is that the clouds run on what I would call an evergreen model of procurement. That is, they are always buying new hardware and installing new hardware and retiring old hardware. And the HPC systems, partly because they want uniformity, are mostly running, they have 1 or 2 big systems in a particular HPC facility, and you'll run those for 3 to 5 years. And now we did a study on this also back around the time of the Magellan study. One of the, actually my deputy for operations at NERSC did a study to look at the cost of ownership of these systems. And at that point in time, Moore's law was still pretty healthy, even though we were starting to see, of course, multi-core and the end of Dennard scaling. But it was the case that after about 4 to 5 years, it was actually cheaper to go buy new hardware than it was to run the old hardware, because the amount of power that it took to power the old hardware, and you started, just that alone meant that the power and space and everything, you could buy something that was much smaller and much more energy efficient and had the same performance in about 4 years. That could replace the old hardware. So there was no point in running them longer, but we do run the HPC systems, and now the lifetimes are getting somewhat longer because that has slowed down, right? The pace at which something is getting more energy efficient has slowed down to some extent, but it was still the case that an HPC center is going to buy new hardware, let's say every 4 years. And so in between that time, if you're accessing the system, because they tend to buy high-end processors, you can get the latest hardware for the first year or so, and then you have to wait another 4 years until you get the latest hardware. Whereas in the cloud, if you're willing to pay for the very high-end instances, you can always get access to the latest, say, GPUs or other computing hardware. So she also looked at the memory bandwidth, and this is it shows the performance of the stream benchmark. So looking at memory bandwidth, and these are 4 different operations here across the x-axis, but in each one of these, the peak is the Cori KNL system has the highest memory bandwidth. And that's probably because the high bandwidth memory modules on there. And if there's no on-chip memory, then the cloud instances have higher memory bandwidth than the Cori system. So this is getting at the issues of having local disk and so on. And so the faster hardware turnaround can benefit both the compute-intensive workloads and the data-intensive workloads, because you get these memory advantages as well as seeing the compute advantages. So that Haswell system is looking a little out of date at this point. KNL is, as I said, just a little bit of an oddity, but Haswell is sort of a standard high-end processor, but it's not as recent as the processors that are in the AWS systems. And then she looked at application benchmarks. So this is looking at n-body. So this is a naive n-body where you're doing all-to-all computations between all pairs of particles, and an FFT with strong scaling. So each of these are strong scaling. So a fixed problem size running on up to 8 nodes. Now notice this is a pretty modest number of nodes. And so that's going to be an open question here, which I think many of the cloud vendors who've started to see these results have been interested in, is what happens if you run at a larger scale. We were doing this without too many cloud credits available. And it does take time still, I think Julia can maybe say, to try to get these larger jobs launched on these systems. And there are, but you can see from this that the n-body is doing pretty well on these 2 AWS systems here, and the KNL system is noticeably lower and actually not scaling as well. This is probably you're seeing some communication issues here, and then the FFT, you see somewhat different behavior in terms of and that breaks down the communication. The computation is really an issue, since the FFT is very compute bound, as you've heard. Okay, so let's talk a little bit more about the underlying the systems between these, and I'll just say we used to talk in this lecture, which has been given now for let's see, at least 5 years, I guess, about the particular configurations that you could buy in the cloud. So one of the big open questions still about Julia's study and many others that we all get asked about is the price of these different things. And I'm not going to try to do a price comparison. I did one actually around the time of the Magellan Project. And at that point, it seemed like there was a factor of about 3 to 5. And those are the kinds of numbers we're still seeing. And if you look at, for example, the cost of buying the instances that Julia was running on relative to the cost of running NERSC for a year, and you tried to buy sort of a year's worth of computing time. Whether or not that's a fair comparison, I guess, is one of the reasons that people are reluctant to do these cost comparisons. So one of the things that you have in the cloud is you get on demand, but you can also do spot pricing where you can get access to lower cost hardware if you're willing to sort of run your jobs at the time when they're going to be the cheapest. So the price of a cloud access is going to vary over time. And so you can go and buy it at that lower price if whatever work you're doing is not time sensitive. So this is something the scientific computing community in some cases is quite sophisticated at, some of the biology community and some of the high energy physics community. And what they do is they don't ever buy sort of on demand pricing in the cloud. They'll go and they will go and access, just wait till the spot pricing gets to a certain level and then run their backlog of, say, data analytics jobs from the Large Hadron Collider or whatever at that lower price. So in 2014, when we first started giving this lecture, this was the cost per hour of a few of these different instances. So about 2 cents for the smallest instance up to about $2 and 40 cents for the larger instance. And there's now over time, and I've skipped some of the intermediate years, although they're all in the PowerPoint slide if you want to see how things changed over time. By 2018, it was down to less than a cent per core hour, and about 0.6 cents per core hour for this sort of comparable looking, what was called a nano instance at that point. And then, some of these other prices which had made recent changes are crossed out here, and then up to about $14 then for the high-end instances. Now, this one has 16 NVIDIA GPUs on it. So those get to be very expensive nodes. And this is what, I've spent some time talking with people across campus in my associate dean role about use of the cloud for, a class like, so let's say Data 8 that's running Jupyter Hub inside of the cloud. They're running at less than $1 per semester, or a couple dollars. I think they're trying to get it under $1, but a few dollars per semester per student for that kind of workload. So it's really quite minimal in terms of the cost in the cloud, but they're not doing very much compute intensive work, and they don't really, and they can be running on pretty small instances. On the other hand, a class that's being taught, a master's level class that's being taught in the iSchool, where they're really doing deep learning and in particular running training algorithms and stuff like that, they run, they're spending $100,000 per semester for a much smaller number of students. And so you really get to much higher costs. And that's anecdotally is what we hear from people within, say, the RISE lab and the Bear lab and things like that, that they're running at many thousands of dollars, maybe $100,000 per year per student for a student that's working on deep learning. So that's causing people to not want to use the commercial clouds if they unless they can get time for free, which some of the labs do. But if they actually have to pay for these instances. Okay, so let's look. This was a little bit then now comparing Hopper, which was the machine before, actually 2 machines before Cori. So it was Hopper, then Edison, then Cori, and what those machines looked like in the data center sort of at the time. There's you can see the data center at this point was already starting to grow to, although not a lot far higher, it was say 10,000 to 100,000. Sorry, 1,000 to 10,000 nodes, whereas Hopper had a comparable number of nodes, about 6,000. Slightly more cores per node, but not a huge difference in terms of an HPC system versus a data center system. And the memory per node also, the slight advantage here to the data center. And the storage overall was quite different in terms of much higher level storage, a much larger storage in the data center. On the other hand, a much higher speed interconnect network. And then in the Cori phase 1 system, when that got installed, the Haswell system, you can, I won't read through all of the differences here, but you can see that at this point, you know, the number of nodes here was actually a little bit smaller. That's just because Cori was just the phase 1 system. Some of the other numbers, the storage system started to grow at that point, and the networks were kind of comparable. And then entered the Xeon Phi, and we got up to, once again, you know, 9,000 nodes and a lot more cores per node. And that it's not clear. So that I think the data centers now are getting to the point where they're putting in things with, say, 64 cores per node, at least 32 cores per node. But the other main point of this is that in the cloud, you can basically buy whatever you want, right? If you want a very high-end system with lots of memory per node, or you want something with lots of cores per node, you can have access to them because there's such a huge and enormous variety of the types of things you can buy. Whereas the HPC systems, because they want to be able to run jobs that are uniform across the system, they really need to not have too much heterogeneity within the systems. And so Cori is a little unusual in that it's got 2 partitions that have different types of processors, but, and what that means is, by the way, we don't run the LinPack benchmark, for example, or any other real application across the entire machine with both Cori and both Haswell and KNL nodes. And of course, you can get GPUs in the HPC systems as well as in the cloud instances at this point. So all of this is to say that from a hardware perspective, I think that, and you can see this from Julia's results, where the cloud systems have really started to catch up with the and even exceed the performance of the HPC systems at the scale at which she was running. So I think it's very important to keep that in mind. Now we've heard that, you know, the clouds are putting in we know that they put in these high bisection bandwidth networks across the facilities in order to be able to move the data around and things like that. So that may come up again, you know, so it may be that bisection bandwidth, if you can actually get a large enough, and by the way, she was using HPC instances, so things that were optimized with batch scheduling for batch scheduling sorts of workloads. And that has interest in that in the commercial cloud has increased because of interest in things like deep learning training. Okay, just a little bit of an aside on the facilities and what they have looked like over time. So one of the things that we worry about a lot is the amount of power that's required, or the total energy bill for one of these. And there's a group at Lawrence Berkeley Lab that looks at the energy efficiency of data centers in particular. So what are the goals if you're designing and building a data center? Well, you want to take advantage of the economies of scale. That is, that the number of staff you have, that you have at a particular facility are going to be kind of amortized over that facility if that facility is larger. So there are certain things where, for example, at NERSC, we have an operator on site 24 hours a day. And there's a certain cost to having a person there 24 hours a day just to make sure. And you could say, well, why don't we just put in sensors that have smoke detectors and electrical detectors and flood detectors and all these other kinds of things, which you could do. But having an operator there means that if anything sort of physically happens with the facility, there's somebody to immediately turn off the machine, which you might not want to have decided automatically. So one of the other things that people worry about a lot in designing these facilities today, which they didn't worry about 15 years ago, is the energy efficiency of the data center. And work that the LDL group has done on PUE and the power usage effectiveness is, and I'll show a graph on that in a minute, looks at how efficiently are these facilities. There's a cost efficiency of the center and how much it costs to run the facility, the cost of the power, so each of these big facilities are built at places where you can get fairly low cost power. That's true, by the way, in both the cloud and the commercial cloud and the DOE HPC facilities. So at LDL, we get lower cost power than the campus does because it's part of one of the national labs. And that's actually fairly clean power, relatively speaking, even within California's general mix of power. And of course, the cloud providers build in places like Washington where they can get relatively inexpensive and very clean hydropower. But there's a limited number of places that you can put these facilities as well. But cost efficiency is one of the things that they look at. And then using, whether or not you're going to customize the design of the machines. So what is this PUE? PUE is this power power utilization efficiency, sorry, I've forgotten, power usage effectiveness. I always just refer to as PUE. So the PUE is the percentage or of kind of overhead of the power used in the center relative to what it takes to just turn on the racks. So you look at the power that the racks draw for the computing and the storage in the facility. And so you measure that total amount of power draw, and then you look at the amount that the building is drawing, and then you look at the fraction of that over 1. And so it would be a perfect PUE would be if you had absolutely no overhead, that the amount of power you were drawing was just equal to what it took to power the racks. And so you can see that you know, these PUE numbers of 22% or so are showing here at kind of an average. Now this sawtooth is because it's the different times of year, right? So in the summer you have a much higher PUE because you're running all of this power to run the cooling systems. And then when it's winter, it's cooler. One of the big advantages of running a data center in Berkeley is that you can use free outside air cooling, because it's still pretty cool in Berkeley, although we do have some hot summer days. And in fact, on those hot summer days, the cooling that's in the Nurse Center is based on cooling towers, and so an evaporative cooling. So usually in Berkeley, when it's hot, it's also dry, and so the evaporative cooling is very effective. But they actually did have to slow down the queues when it got super hot a couple of years ago. Of course, there were also the power outages, but that was a different thing when they. And so this is the comparison. So this study really has the big data centers now, the big cloud computing centers all run at a PUE of somewhere around 1.1, a little bit over that 1.11 or whatever. So somewhere close to about a 10% overhead. And the same is true for NERSC, and the same is true for the commercial clouds as well. A lot of the, say, university data centers or ad hoc data centers that are set up in people's laboratories, so an individual PI data center, they probably would have a PUE of more like 1.7. So you don't even see that on this graph here, but a lot of the data centers that were originally studied by LBNL had a PUE of more like 1.7 or 1.8. Okay, and so let's see, in terms of the supercomputing center, so this is what the building looks like. We used to be able to take people there. It was it's a 12.5 megawatt facility, but it's in the process of being upgraded to 25 megawatts. In fact, it is probably technically at 25 megawatts at this point, or it will be within a few months, and that is getting ready for the Perlmutter system, which is also in the process of being installed. All right, but you know, one of these data centers, such as this one in Oregon that I showed a picture of earlier, is going to be even larger. This one has 3 of these different buildings for the data centers themselves. This 4th building is, I think, probably for people or whatever, for other things, and maybe equipment. And this is a 200,000 square foot building, so huge flat big spaces. By the way, this building you can't see it so well here, but this is a very steep hillside. This is if you stood in the middle of Hearst Avenue outside of, say, in between Soda and Corey Hall someplace, which I don't recommend you do because it's a fairly dangerous place to be, but if you stand there and look up the hill, you'll see this building, which is Wang Hall at NERSC. And so this is 27,000 square feet of computing center space. So pretty big data center, but not 200,000 spread out over 3 buildings. And nevertheless, you get some of the economies of scale in both cases, right? So you certainly probably get some additional ones here, and they buy power in bulk in both cases. The DOE buys power in bulk, and they do as well, so they get some of those advantages. Yes. The bus, Julia says that it is very steep. So yeah, it's about a 15-minute walk in either direction, but only walk it if you're feeling like you really want to hike uphill, and bicycling is even harder. But the buses that go up the hill have a bike rack on the back, so you can hang your bike on them. And in the interest of making these data centers green, places like Google and other big cloud providers, of course, are looking at renewables, not just hydro, but there's a big solar farm, 30 megawatt solar farm that's in the Netherlands. Okay, so a little bit more about software. So I talked about the programming model and in the cloud and the Hadoop and then Spark programming model. But let's do a little bit of a side-by-side comparison between MPI on the HPC side and Spark and Hadoop on the other side. So what's really the difference between them? And we'll talk a little bit about doing scientific computing on Spark. We'll talk about running Spark on HPC systems. I've already shown you some of the results of running HPC jobs on clouds and on non-cloud systems and on HPC systems in the comparisons. So we're going to, in Spark, they'll want you to use the native operations rather than writing directly in Spark at this higher level. And so using built-in optimized libraries such as the BLAS, and there's somewhat limited communication models from the programming model that you've got this shuffle operation that is used for most of the communication. You don't have a lot of the other facilities. So let's kind of go through this. Just reminding you of the data parallel programming model. So let's do a side-by-side comparison. Okay, so MPI was really designed with high performance in mind. MapReduce is designed for convenience. And so those were very different perspectives going into it. At the time MPI was designed, it was because there were already a plethora of different message passing libraries that the scientific community, had developed, and there was the chemistry message passing model and the physics message passing model and all of these different versions of it from different universities and so on that were competing with each other. So this was a standardization effort. Whereas MapReduce really came from this idea, well, we've got big data problems we're trying to analyze. Let's figure out what is convenient. So a SPIMD parallelism model in MPI. Now I have to add a caveat that one of the developers of MPI, Rusty Lusk, will always say, no, it's not fair to say MPI is purely SPIMD because you can do other things. You can have communicators, right? You can divide things into groups. It's not fixed that you can only have sort of a fixed number of processors all executing the same program, and there are other ways of doing things in MPI. But for the most part, most MPI programs are written as this sort of flat one process per node. Now you might put some OpenMP inside of it or whatever. MapReduce, on the other hand, is really more of a data parallel model. It's just a set of global operations that then get mapped onto the distributed memory hardware for you. And it's that restrictive but very convenient programming model that also allows you to do an implementation. MPI, of course, you manually control the data layout and you manually are in charge of all of the communication, whereas all that's automated for you for the most part, in MapReduce. Now, we did see that in Spark, you've got some hints to put into the program for things like caching. So those are locality optimizations that you're putting into Spark. And the communication, as I said, is really this one shuffle operation or this reduce operation in MapReduce, whereas in MPI you have both collective communication and point-to-point communication. And if you really want point-to-point communication for a particular algorithm, it is a little bit awkward or inefficient in a MapReduce model to get something like that. MPI does not have built-in support for automatic fault detection, correction, resilience, or for automatic load balancing. We've talked to you, and we'll talk to you more Thursday about load balancing and all the different techniques that you can use at the application level on top of MPI to give you better load balance. There are versions of MPI that are built that have features for building fault resilient applications in the high performance computing community. And we haven't talked about this, I think, very much, if at all, that what people do in applications, which tend to be things like simulation problems that are time stepping, is they'll run a certain number of time steps and then they will dump out the state. And that's actually fairly efficient because as an application programmer, you know what state variables are needed to reconstruct that execution at a given point in time. Whereas if you just snapshot the total working set of the memory of the application at an arbitrary point in time, you might need to save a lot more state. So, once again, MPI is all about performance and efficiency, but a lot more work for the application programmer. MapReduce, of course, is handling these faults for you automatically and can tolerate them, and to some extent can tolerate a certain amount of load balancing. And so Julia says she hasn't heard of somebody trying to do this. I assume you mean a checkpoint restart. Is that what you mean? Or And
Oh no, I was thinking more like
the
trying
big
to
code,
like actually put
codes like
together.
the
Yeah.
climate models absolutely do checkpointing and restarting. And it is, from having worked on some of these codes that do that, I will tell you, it's all of the problems that I mentioned earlier with MPI and the loss of type checking. When you checkpoint, you're dumping a bunch of bytes out into a file, and you got to make sure you can read them back again when you need them. And so it can be, it's ugly, tedious code to write. Okay, so here's another study that was done then comparing the programming models now. So this is not comparing the hardware. So the previous study that Julia did was comparing the hardware. And although 10 years ago, it looked like there's a pretty big gap in the commercial cloud in terms of they were much slower. Now they actually have an advantage because you can tend to be able to get access to newer hardware in the cloud than you have in a given HPC center, unless you happen to be using an HPC center that's just upgraded their hardware. On the other hand, once you look at something like programming at the Spark level, there is a lot of overhead in Spark for all of this resilience. And this is looking at doing a non-negative matrix factorization, so a machine learning algorithm on over a terabyte of data from a nuclear science study, the Diabé experiment. And so it's a 1.6 terabyte matrix that's doing non-negative matrix factorization on. And what we're looking at here is Spark versus MPI in each group of 2 columns. And so this is running time in the y-axis. So you can see the MPI is faster than even just looking at the file IO, the HDFS read, plus the actual tall skinny QR, which is used inside of that's what's inside the solver, and then X-ray, which is a little bit of the other computation that you can barely see here. So those blue and green bars. So there's a noticeable advantage, a little bit less on this this third group these are 3 different size configurations. Sorry, these are different node counts. So 50, 100, and 300 nodes. So the gap is getting a little bit lower here at the 300. And but there's also some pretty big overhead to starting up the tasks and the scheduler in the case of Spark. And this is looking at another time for running PCA, so principal components analysis on a ocean matrix. This is running on Cori. And so these are, you can see there's some slowdown here again from Spark relative to MPI. Okay, and let's see. So the other thing, and this previous one was looking at Spark running on an HPC system, but there was another study done looking at Spark on an HPC system, and I think a high level conclusion too that I want to just point out is this. So remember back on Jeff Dean's lists of running real clusters in problems of running real clusters in the real world and all the different problems he had, and the fact that disk failures are actually much more frequent than node failures, than CPU failures, or than memory failures. So when you have failures, they're often in the disks. And so when you've got a cloud system that's got a bunch of local disks on it, those nodes are going to fail much more frequently than the nodes in an HPC system that don't have any disks attached. Now, that said, the file system at NERSC, and by the way, Cori is down today, so you'll probably be seeing a note about an extension a little bit later for homework 3, once again, is going to be, the node failures are going to be somewhat lower. On the other hand, if anything ever dies in NERSC, it's almost always something related to the file system. So that tends to be the, not just because of the hardware, but because that software is quite complicated as well. So at least when I was NERSC director, that was 90% of the problems we had were with the file system. Even when it seemed like the compute system was down, it was often a problem with the file system. And so what we're seeing here is that the design of Hadoop and then the design of Spark were really set up for systems in which you assume the nodes fail. And the nodes do fail with higher frequency because you've got disks attached to them. An HPC system, you assume the nodes don't fail. And although the system seems to be going down with some regularity, it's not really individual node failures. So it's not as though the individual applications could necessarily recover from those node failures. And so there's an assumption that things are highly reliable in the HPC world, and an assumption that they're not in the cloud world, and that adds overhead to the cloud programming model, and it adds lack of resilience into the HPC model. Okay, so this other study I was just going to look at is looking at the comparing, where really does the problem come from in running Spark on top of an HPC system. So this is looking at a workstation. Here's the first two sets of bars. The Edison, so an older, that was the system in between Hopper and Cori, so the one that was just turned off, alas, right before in getting ready for Perlmutter. I think they could have left it running a little longer, and then Cori. And so what you're seeing here is both running Spark when it's running on disk and running on memory mapped. So when it's not actually going out to the file system, which is, because disk in this case means going out to a remote file system that is part of the HPC facility, but not attached to a local node inside of the system. So the workstation has a definite advantage if you're going to run if you're using that file system, right? And so that's what this study says, is running Spark is kind of a pain. It's not a good fit for an HPC system which has a remote file system. On the other hand, once you memory map it, then you can, and you are actually doing those sort of Spark operations inside of the memory that's associated with the nodes, you can get that performance back. Okay, so I'm going to just sort of wrap up now and talk about just to summarize the cloud versus HPC part of this. And I will say that since I first put this slide together, it looked a little bit different more than 10 years ago, around the time of the Magellan project. And when I was giving a talk, some of these things were much more clearly distinctions. So on the cloud side, we have a focus on storage and data. On the HPC side, when you're designing the systems, you're focused on computing and floating point operations. Now, what has changed is deep learning algorithms, convolutional neural nets in particular, being dominated by dense matrix multiply, which have forced compute intensive considerations in the cloud, at least in some of those instances. And a lot of data intensive applications actually, such as genomics, which you'll hear more about from Aiden, but both Julie and I have talked a little bit about in the HPC community as well. And a lot of work on running other workloads, the telescopes and things. I think Julian Burrell will be giving a talk in a week or so on some really interesting work and his experience running HPC applications for data analysis from looking at cosmic microwave background. So the cloud was buying the cheapest commodity components originally, whereas HPC was buying the highest end components, and sometimes there was some hardware specialization, as in the T3E. HPC has gotten more commodity over time. They certainly don't just build special purpose vector supercomputers, whereas, and the cloud has put in more sort of cutting edge hardware, which is why you can now, why they have an advantage now if you pay for the most expensive instances in the cloud. Commodity networks, I mean, they were Ethernet networks, and now you can get InfiniBand networks in the high-end HPC instances of the cloud. High performance instances of the networks have always been the case in HPC. And continue to be. And although actually the Summit machine at Oak Ridge is also an InfiniBand network, so not exactly commodity, but is used in also in the commercial clouds. Pay as you go versus purchased for a particular mission space, like the Department of Energy's Office of Science mission space. And what you pay for as a user, what we are paying for all of the work that you do in this class in NERSC is we're paying in hours, and we don't pay for those. We don't pay in cash for those. We got a certain allocation of time. If one of the students, one of you in the class uses a whole bunch of time, and we've tried to give you limits to make sure you don't use everybody else's time in the class, but sometimes things go awry, that we can't turn in the leftover time at the end of the semester and get cash back from NERSC. Whereas in the cloud, if you don't spend it, then you've got your cash. The clouds are run at typically at under 50% utilization. That's why they sell spot pricing instances, sometimes at a loss, because they would rather, because that is going to sit there idle if they don't sell it. And so that's what causes it to actually be cost effective to then go and run things in the spot prices if they've dropped to a low enough level. Whereas the HPC systems run at 90% utilization, and that's because your jobs sit in the queue, especially your larger jobs. They're going to wait for quite a bit of time. Your smaller jobs in this class, some of them you can run almost on demand, but you do see that you're running things, you can do things interactively, but a lot of the workload is running in queues. And that's because that's what allows us to run at 90% utilization, is that the scientists are willing to wait for their jobs, and the government agencies that fund this don't want to see the computing time wasted. I don't know why they care more about the computing time than the time of the scientists, but that's the way, that's the sort of economy in which we live. And they do put multiple jobs on a node in the cloud. This is something NERSC is actually working on for the GPU nodes, but the model in HPC has always been a dedicated node for a particular user's job. So you don't put multiple jobs on a node, but that may be changing under Perlmutter. And then the cloud systems were mostly, because they had disks, they had to keep those nodes fairly cool, and they were air-cooled systems, so they're not nearly as dense. Whereas an HPC system, if you're trying to get a really low latency network, you got to pack the system together, and that has led over the last decade or so. So when I first became NERSC director in 2008, we had air-cooled systems, and then over the next few years, they became liquid-cooled, and now the HPC systems are predominantly liquid-cooled. And cloud systems, I think also, if you've got a big GPU system, I'm sure those are liquid cooled. I mean, even my son's game system on his desktop has liquid cooling in it. But for the most part, a lot of cloud systems, at least those original data intensive system with lots of disks per node, they would be very sparsely populated, and therefore they could be air cooled. So I'll just point out that I think the most important differences, that almost all the technology differences have disappeared. And what is left is actually the business model and kind of policy differences, how you pay for it, how you run it in terms of utilization, whether you're going to expect on demand turnaround, or you're going to expect for your jobs to wait. And that's related to the utilization number. And then whether you have, whether you're scheduling multiple jobs or have dedicated jobs, which really does affect your load balance and your expected performance, right? Once you start sharing jobs, you've got to expect that your individual cores on that node, even if they're dedicated to you, are going to run at different speeds if other cores are sharing your memory system. So those are really, in my mind, the important differences are not the technology differences anymore, but the policy and business model differences. All right, and I think with that, I will wrap up. We're out of time, a minute over, and thank you very much. Aiden and I will both be back on Thursday talking about graph partitioning and other forms of dynamic load balancing. So we'll see you then. Thanks a lot. Bye.